Welcome to the Deep Dive, everyone. Ready for another deep dive? This time, we're going to be exploring the world of connectionism.
Absolutely, yeah. It's a fascinating field where science and tech kind of collide, really.
Right at that intersection, we're talking about like reverse engineering the brain
Yeah.
to build smarter machines.
Yeah, and it's a completely different way of thinking about AI, instead of programming computers with like, all these rules and stuff, connectionism.
Yeah.
It aims to kind of develop systems that learn from data, right? Mirroring how our brains work.
Well, and we know the brain is just this, insanely complex network of billions of neurons all interconnected. How does that translate into the world of machine learning? What are we talking about here?
Well, imagine a vast web of connections, right? And they're constantly adapting and changing based on the information that's flowing through them. So each connection, its strength determines how that information is processed and ultimately, how the network learns. And that's what connectionists are trying to replicate, that dynamic learning process of the brain within a computer system.
So instead of static instructions, we're talking about systems that evolve and adapt as they're fed information. Are we essentially trying to create like artificial brains here?
Well, it's a bit more nuanced than that. While we're drawing inspiration from the structure of the brain, connectionist models are still fundamentally different.
Okay.
We're building artificial neural networks, these complex structures of interconnected nodes that mimic the way the brain learns and processes information.
And how do those networks actually learn? What triggers that process?
The key is the backpropagation algorithm.
Yeah.
Think of it as a sophisticated feedback loop,
Okay.
The network makes a prediction based on the data that it receives, and then it gets feedback on how accurate that prediction is.
Yep.
And using that feedback, the algorithm adjusts the connection strengths between those nodes. It's essentially fine-tuning that whole network with each iteration.
So unlike traditional programs that follow a fixed set of instructions, these networks are constantly refining themselves, learning from their mistakes, and becoming more accurate over time.
Exactly, yeah. It's a dynamic process of adaptation and improvement driven by data and feedback, and it leads to some truly remarkable capabilities.
And this is where it gets really interesting, right? How are these networks actually applied to solve real world problems, to actually predict outcomes in practical ways?
Well, one of the most common types of neural networks is called the multi-layer perceptron.
Okay.
It's a hierarchical structure with layers of interconnected neurons, each layer sort of extracting increasingly complex features from the data that it receives.
Okay.
And this allows it to learn intricate patterns and relationships, making it really suitable for tasks like image recognition or natural language processing.
So each layer is like delving deeper into that data, extracting features and patterns that simpler models just wouldn't be able to see, right?
Exactly. But the world isn't always so straightforward.
Right.
Relationships can be nonlinear, meaning a small change in one area can have like a huge impact on the outcome. And that's why connectionists use nonlinear neurons in their models.
That makes sense. If we're trying to mimic the complexity of the human brain, we have to account for those nuances, those unexpected terms.
Absolutely. These nonlinear neurons, they introduce this crucial element of flexibility into the network's calculations. They can capture those intricate interactions and relationships that traditional linear models just can't handle.
So it's about going beyond the limitations of those simple linear models to create something that more accurately reflects the complexities of the real world.
Precisely. By introducing that nonlinearity, connectionist models become much more adaptable and accurate. Particularly when you're dealing with complex real-world phenomena.
This is all incredibly fascinating. I mean, we're starting to kind of unravel how connectionists are working to replicate the brain's learning process in machines, but we've only just scratched the surface here, haven't we?
Oh, there's so much more to explore. The world of connectionism is vast, and we've really only just begun our journey. I'm looking forward to diving deeper with you.
So we've talked about how connectionists are like drawing inspiration from the human brain to create these powerful machine learning models. But the brain's efficiency is just unparalleled. How do they even begin to replicate that level of complexity?
Well, it's a challenge, that's for sure. But one approach is to actually harness the power of evolution itself within a computer. We call these genetic algorithms.
That sounds intriguing. Are we talking about like survival of the fittest, but for algorithms?
You've hit the nail on the head. We start with a population of potential solutions. Each one represents a different approach to solving the problem. And these algorithms then undergo a process of simulated natural selection, random mutations, combinations, that sort of thing.
So over time, the most effective solutions kind of rise to the top, just as in nature.
Precisely, yeah. Over many, many generations, the solutions are refined. They become more and more effective at tackling the problem at hand. It's a fascinating way to leverage the principles of evolution for problem solving.
That's incredible. But isn't that incredibly time consuming, I mean?
It can be, but
Right.
but remember that computers operate on a vastly different timescale than biological evolution.
Right.
We can simulate eons of evolutionary processes in a fraction of the time.
So we're essentially accelerating evolution to refine our algorithms,
Right.
like fast forwarding through, millions of years of natural selection.
That's a great way to put it. And the applications are far-reaching too. Genetic algorithms have been used to design everything from antenna configurations for spacecraft to optimizing, complex production lines in factories.
So we've already discussed backpropagation, that feedback loop that helps neural networks learn.
Yeah.
Is there any way to kind of combine that with genetic algorithms?
That's a great question, and it leads us to an even more powerful concept.
Okay.
Imagine using genetic algorithms not just to refine those solutions, but to actually design the structure of a neural network itself.
So the genetic algorithm would act as the architect, crafting the blueprint for the network, while backpropagation handles the fine-tuning.
You've grasped the concept perfectly. It's a powerful synergy. It allows us to leverage the strengths of both approaches to develop even more sophisticated models.
So we've discussed replicating the brain's structure, its evolutionary processes. But human thought, it goes beyond simple calculations, right? I mean, we deal with uncertainty, intuition, probability. How do connectionist models even begin to address that?
Well, that's where the Bayesian approach comes into play. It's about incorporating those elements, probabilities, uncertainty, directly into our models.
So instead of just definitive true or false statements, Bayesian models deal in shades of gray.
Exactly. They work with degrees of belief, assigning probabilities to different hypotheses based on the available evidence.
So it's like saying this is likely true based on what we know, but we're open to new information that might change our assessment.
That's a great analogy. Bayesian models are constantly updating their beliefs as new data emerges, just like, a detective refining their theories as they uncover new clues.
This seems incredibly valuable when you're dealing with incomplete or noisy data. Situations where traditional models might just falter.
Absolutely. Bayesian models excel in handling that uncertainty, and they can even incorporate prior knowledge into their calculations, much like humans draw on their past experiences.
So it's not just about crunching numbers. It's about incorporating the nuances of human reasoning into these models.
Precisely. And the applications are far-reaching, from filtering spam emails to aiding in complex medical diagnoses. Bayesian models are proving their worth in a variety of fields.
This is all incredibly mind-boggling. But I have to confess, my brain is starting to feel the weight of all this information. It's like we're trying to condense centuries of scientific progress into a single deep dive.
It's understandable. Connectionism is a vast and intricate field, and we've covered a lot of ground, but don't worry, there's still more to explore, and we're just getting started.
We've really gone deep into the mechanics of these connectionist models. I mean, neural networks, backpropagation, genetic algorithms, even Bayesian models. It's remarkable how these concepts are all intertwined.
They are, yeah. And as we kind of explore further, you'll find that analogy plays a really crucial role in how we understand and utilize these models.
Analogy, you mean like drawing comparisons? Like this is like that?
Exactly, yeah. Analogical reasoning, recognizing similarities between things that seem completely different, so we can make inferences, predictions. It's really a cornerstone of human cognition, and it turns out it's incredibly relevant to connectionism as well.
That's fascinating. Can you kind of elaborate on that a little bit? Like how does analogy fit into all of this?
Well, think about how we as humans approach, new situations. We often draw on our past experiences, right? We look for parallels that can help us understand the present. We use analogies to bridge the gap between what we know and what we don't know.
So we're essentially looking for those patterns, those familiar kind of pieces of ground that can help guide our understanding.
Exactly, and that's a concept that translates beautifully to the world of machine learning. One of the earliest machine learning algorithms, called nearest neighbor, is based entirely on this principle of analogy.
And how does that work in practice?
Well, imagine you're trying to classify a new data point, say an image of a handwritten digit. The nearest neighbor algorithm would compare that image to a database of previously classified images, and it would find the one that's most similar.
So it's like finding the closest match and using that as the basis for classification.
Precisely. Yeah, it's a simple concept, but it's surprisingly effective, particularly when you're dealing with complex data where defining those explicit rules is really challenging.
Makes sense. But are all analogies created equal? I mean, are there different levels of sophistication when it comes to this analogical reasoning?
Yeah, that's an astute observation. Nearest neighbor, while effective, operates on a relatively surface level. It focuses on those readily apparent similarities. But more sophisticated approaches can delve deeper. They can explore the structural relationships within that data.
So rather than just mashing features, these advanced techniques are looking for deeper correspondences. They're looking for patterns in the relationships themselves.
Exactly. One such approach is called structure mapping, and instead of just comparing those features, it tries to map the relationships between those features in two different situations.
Can you give me an example of that?
Sure. Consider the analogy that's often drawn between the solar system and an atom.
Right, the classic.
Yeah, both have a central body, the sun in one case, the nucleus in the other.
Yeah.
And they have these smaller bodies orbiting around it.
Right. But structure mapping goes beyond that simple resemblance, right?
It does, yeah. It delves into the relationships. So the gravitational force between the sun and the planets, that's analogous to the electromagnetic force between the nucleus and the electrons. It's about finding those deeper, more nuanced correspondences.
That's a powerful concept. By understanding that underlying structure, we can draw more insightful connections and potentially even transfer knowledge between completely different domains.
Precisely. Analogy is a powerful tool both for human understanding and for building more intelligent machines. It allows us to bridge those gaps, transfer knowledge, and make sense of this complex world around us.
Well, this entire deep dive has been an incredible journey. I mean, we've explored the inspiration behind connectionism, the intricate mechanics of neural networks. We've even touched on some of the philosophical implications of replicating human thought processes in machines.
It's been a real pleasure exploring these ideas with you. Your curiosity and your insightful questions have made this a truly engaging conversation.
Well, thank you for sharing your expertise and really your passion for this field. And for all of you deep divers out there, we encourage you to like, share, and subscribe for more fascinating explorations into the world of knowledge and ideas. Until next time, keep those minds engaged and keep those questions coming.